Assalamu alaikum. Welcome to the next class. In this class, we'll be dealing with the power in AC circuits. Already we have done a lot in case of AC circuit. We have discussed the resistances, inductances, capacitances. Now we'll discuss how the power is supplied by the AC source to these circuit elements. Let us first discuss about the instantaneous power. The instantaneous power, which is denoted by PT, absorbed by the element, is the product of the instantaneous voltage Vt across the element and the current through it It. So Pt is equal to Vt into It. The instantaneous power in watts is the power at any instant of time. It is actually the rate at which the energy is absorbed by the circuit element. Now, in general, let us consider a circuit element who is excited by a sinusoidal excitation, and let the voltage which is appearing across this circuit element is Vm cos of omega t plus theta, theta V. Theta V means which is related to the voltage, and It is Im cos of omega t plus theta I. So again, this is this is the angle of the current with respect to the reference, some reference. This is the angle of the voltage with respect to the same reference. So where Vm and Im are their respective peaks, and the instantaneous power given by the product of Vt and It will be Vm Im cos of omega t plus theta V cos of omega t plus theta is simply multiplication of these two. So using the relation cos of A and cos of B will be equal to 1 by 2 cos of A minus B plus cos of A plus B. So cos of A minus B, that means this will be, let us say, A, this will be minus, this will be B. So A minus B will be equal to omega t, and omega t will cancel out. It will be theta V minus theta I. So it will be equal to Vm Im divided by 2 cos of theta V minus theta M. You can see over here Vm Im by 2 cos of theta V minus theta I, and then A plus B divided by cos of A plus B, simply cos of A plus B. So it means it will be equal to cos of 2 omega t plus theta V plus theta I. So it will be Vm Im by 2 cos of 2 omega t plus theta V plus theta I. So you can see we have two parts for this instantaneous power. One which is independent of the time. There you not see any time variable, so it will not depend on the time, and the other one which is dependent upon the time. The independent value depends upon the difference of the phase angle between voltage and current. You can see over here. So this second part, it has a frequency of 2 omega. It means it will vary as the frequency 2 omega. Omega is the frequency of the voltage or current. So the frequency of the power component over here, and it will be actually the frequency of the whole P of t. It will be 2 omega t, that means twice that of the frequency of voltage or current. So when a sketch is drawn for this, for different values of Vm, Im, theta, Vn, and t is varied, so we get this type of a sketch. So its time period t is equal to 2 pi by omega is the period of, you can see this t actually is the t is equal to 2 pi by omega is the period of the voltage or current. But for the same period, you can see there are two cycles that have occurred for the power. So that means this power is also periodic, but its period is t by 2, or we can see frequency is twice as that of the voltage or current. We also observe that Pt is positive for some part of each cycle and negative for some rest of the cycle. So you can see over here there is a negative part and there is a positive part as well. Positive part will be there when the power will be consumed by the circuit element, and power will be negative when the power becomes absorbed or consumed by the source. So usually when this happens, when the power, instantaneous power, has both negative as well as positive power, the power will oscillate, or we can say it will be transferred from circuit to source. It will oscillate from circuit from source. So the negative power is only possible because of the storage elements like capacitors and inductors. And in general, you will always see that a positive part will be greater than the negative part. And in case of your capacitors and inductors, this positive part and negative part will be equal. You'll never see any case when negative part will be greater than the positive part. And positive part is greater than negative part, that means net power is actually absorbed by the load. There will be some resistance which absorbs the load. So that is the usual case. Now, the instantaneous power changes with time that we have seen, and it is therefore difficult to measure, and we don't know whether this power has to be measured, this power has to be measured, this power has to be measured. So we need to define some other terms so that we can measure the power. So to avoid this confusion, the average power is more convenient, and it is usually the power which is measured. In fact, the wattmeters, the instrument for measuring power, is respond to the average power. The wattmeter actually gives the average power. What is this average power? The average power in watts. Again, this average power is usually measured and calculated in watts. So it is actually the average of the instantaneous power over one period. So the average is given by 1 by t from 0 to t, p of t dt. So actually this t is the time period of the power. It may not be the time period of the voltage or the current. So by doing the same thing, you can see over here 1 by t, 1 by 2 Vm cos of omega t into dt. You can see from here all these things, all these quantities are constant. That's 1 by 2 Vm Im cos of omega t independent of time, and dt will be integrated to t. From t to 0 will be t, and t will cancel out. So it comes out to be this value. But this value, you know that the average of a cos term or a sine term over its time period will be 0 because its negative part will be same as that of the positive part. So in that case, this term will vanish for the average part. So we are left with only with this one, means the average power and the actual power in which we are interested will be given by 1 by 2 Vm Im cos of theta v minus theta I. So writing again this, Vi is equal to Vm cos of omega t plus theta v, It is equal to Im cos of omega t plus theta I. So writing in the phasor form, we just want to find out this power in terms of phasor form. This is actually in terms of the time domain. So V is equal to Vm angle of theta v, that is this V, and I is equal to I m angle of theta I, that is this. So I just find out, I just want to find out the value of 1 by 2 into V into I star. I star is actually the conjugate of the I. So it will be the multiplication of these two, only we have to take the star of this. It is star will be equal to Im angle of theta minus theta I. So when I multiply these two, 1 by 2 is from here, Vm, V has this Vm and this I has this Im, and then when these two angles are multiplied, here is minus theta I because it is star, so it will be equal to theta V minus theta I. So changing it to a rectangular form, it will be equal to 1 by 2 Vm Im cos of theta V minus theta I plus j sine of theta V minus sine of theta I. So why I change it in this form, you will see this form is very important. As we go ahead, we need this. And one more thing, as this is actually the usual form we have calculated just now, that is this. P is equal to 1 by 2 Vm Im cos of theta V minus theta I, that is the same term. So we can recognize the real part of this expression as the average power P. So we can write P is equal to 1 by 2 real part of this V into I star. It comes out to be 1 by 2 Vm Im cos of theta V minus theta I. This is the relationship of the average power that can be calculated. So there are two special cases, actually three. The one is when theta V is equal to theta I. That means when we have already seen this, theta V is equal to theta I, that means circuit element is R, resistance. In that case, the voltage and current are in phase. So this implies a purely resistive circuit or resistive load. So when theta V is equal to theta I, that means theta V minus theta I is equal to 0, or cos of theta V minus theta I will be equal to 1. That means P is equal to 1 by 2 Vm and Im. We may write this in terms of this because Vm is equal to Im into R. So it can be equal to Im square into R, which in terms of phasor will be equal to 1 by 2 I square R. where I is equal to this I into I star equation. This shows that a purely resistive circuit absorb power all the times. So there will be, for a resistive circuit, and theta V is equal to theta I, as I told you earlier, that this average power will be, or instantaneous power will always be positive for a resistive load, and it will consume the power. It will never supply the power back to the source when the load is resistive load. And theta V is equal to theta V minus theta is equal to plus minus 90 degrees. We have purely reactive circuit. If it is plus 90 degrees, that means we have inductive circuit. If it is minus 90 degrees, we have a capacitive circuit, because plus 90 means voltage is ahead of current by 90 degrees, that is the inductive circuit, and minus 90 degree means voltage is behind the current by 90 degrees, that means it's a purely capacitive circuit. And in both the cases, cos of 90 will be equal to 0, cos of plus 90 or cos of minus 90, P will be equal to 0. In that case, we have, as I already told you, that instantaneous power will have equal positive and negative halves. So then average will be equal to 0. Showing that purely reactive absorbs no average power. In summary, a resistive load R absorbs power at all the time, while reactive load L and C absorb 0 average power. Actually, they first, in half cycle, they absorb the power from the source, and then next half cycle they supply the power back to the source. Let us now try one numerical, and it will be slightly easier to understand. Given that Vt is equal to 120 cos of 370 plus 45, here this is the maximum value of the voltage, this is omega, and this is the theta V. It is equal to 10 cos of 370 minus 10 degrees. So we need to find out the instantaneous power and the average power. Instantaneous power will be simply multiplication of these two, or you can generally simply use this formula. That's 11.5. You can directly put the value of this and you can get the instantaneous value of the power. So I will multiply these two using that formula, 1 by 2 cos of A plus B, or directly you can use that formula. So it comes out to be 344.2 plus 600 cos of 750 plus 35 watts. So the average power will be this much. You can see over here from this portion as well, it will equal 1 by 2 Vm Im cos of theta V minus theta I. So 1 by 2 Vm is 120, Im is 10, cos theta V is 45, and theta I is minus 10. It comes out to be this, and it's again equal to 344.2 watts, which is actually the constant part of this instantaneous power. The average power can also be written in terms of the RMS values of the voltage and current. We know that the RMS value of the voltage and current for a sinusoidal value is equal to Vm by root 2, and Im by root 2 for a sinusoidal current, and Vm by root 2 for sinusoidal voltage. So the power that is given by 1 by 2 Vm Im cos of theta V minus theta I can split this 2 into root 2, that is Vm by root 2, and another Im by root 2, that is given over here. So the total, this P will be equal to now Vrms Irms cos of theta V minus theta I. I'll be generally using this type of a relation as compared to this, because mostly whatever be the value that we are getting at our home, that is the RMS value of the voltage or current. Similarly, the average power absorbed by the resistance will be given by IRMS square into R, or Vrms square divided by R. Now, calculate the instantaneous power and average power absorbed by the passive linear network if Vt is equal to 330 cos of A and It is equal to this. This is actually homework. You will try at your home. This is very simple. It's not a big issue for you. It is the similar type of problem which I have just given you, only the values are different. Now we'll come to the apparent power and the power factor. This is very important as far as AC is concerned, because we have described just the apparent power and power factor and reactive power and complex power. We'll start from the apparent power. In earlier case, so in just 2 or 3 slides before, I have told you that Vt can be taken as like this and It can be taken as like this. So in phasor form, V is equal to Vm angle of theta V and I is equal to I angle of theta I. So average power, as we have just saw, it is 1 by 2 Vm Im cos of theta V minus theta I in terms of the peak values, and in terms of RMS value, it is equal to Vrms Irms cos of theta V minus theta I. Let's call this as S. So P is equal to S cos of theta V minus theta I. So we have added a new term, that is S, that S is equal to Vrms into Irms. So this S is actually known as apparent power. So in case of DC, we know that power is equal to V into I. But here in case of AC, we can use again this S is equal to V into I. But apparently it is the power that we are fed to the system, but the actual power that the system is using is something different from this. That is why it is only termed as the apparent power, which actually virtually we can say that is the power, but the actual power that is supplied or that is consumed by the circuit, that is this P, that is S cos of theta of this. That is why this is known as apparent power. So the average power, as we know, is the product of the two terms. The first one is Vrms RMS is known as the apparent power, and the second term cos of theta V minus theta is called the power factor that we have just calculated few slides before. This term is known as a power factor, where power factor is actually nothing but the cos of the angle between the voltage and the current. You can see this theta V minus theta is nothing but the angle between the voltage and the current. So the apparent power, which is, since it's power but it is not measured in power, sorry, watts, it is measured in VA just to distinguish it from the actual power, that is useful power, is the product of RMS values of the voltage and current. The apparent power is so called because it seems apparent that the power should be the voltage current product, by the analogy with DC resistive circuits that we have already done. It is measured in volt amperes or VA to distinguish it from the average or real power, which is measured in watts. The power factor is a dimensionless quantity, since it is a ratio of the average power to the apparent power. We can get the power factor from here. Cos of theta V minus theta I is equal to P divided by S. So that is why what I have written over here. PF is the power factor, P divided by S cos of theta V minus theta I. This is very important. Actually, this power factor denotes how much real power this load is consuming from the apparent power, because apparent power, all the apparent power does not go to the load. Some of the apparent power is also stored in terms of reactive elements. So this power factor is actually a notation that gives us an idea how much real power that is consumed by the load from the apparent power. So again, this theta V and my theta I is known as power factor angle, since it's the angle whose cosine is a power factor. The power factor angle is equal to the angle of the load impedance if V is the voltage across the load and I is the current through it. It's very important. I repeat this, the power factor is actually the power factor angle is actually the load impedance angle, or we can say angle of the load impedance. But one condition is that if V is the voltage across the load and I is the current flowing through the load. So this can be evident from this equation. We know that Z is equal to V by I, where V is the voltage across this impedance and I is the current flowing through this. So Vm is equal to Vm angle of theta V, Im angle of theta I. So Vm by I, Im theta V minus theta. You can see the angle comes out to be the same. Alternatively, since Vrms is equal to V by root 2, that's Vrms angle of theta V. Irms is equal to I by root 2, that's Irms theta I. So Z is equal to V by I, which can be equal to Vrms by Irms, that is Vrms by Irms theta V minus theta I. So again, the power factor is the cosine of the phase difference between the voltage and current. That's what I have told you. It is also the cosine of angle of the load impedance. So this is very important. The power factor may be seen as the factor by which the apparent power must be multiplied to obtain the real power or the average power. So this is already done. The value of the power factor ranges between 0 and unity. This is very important because power factor is equal to this is also the angle of the load impedance angle. Power factor load impedance angle can be 0 when resistant load impedance is resistive. Load impedance can be plus minus 90 degrees when it is capacitive or inductive. When it's inductive it is plus, when it's capacitive it is minus. So this power factor angle ranges from minus 90 to plus 90. We can say minus 90 to 0, 0 to plus 90. At minus 90 to minus 90 and plus 90, the power factor is equal to 0, and at theta is equal to 0, its value is 1. That is why this power factor ranges between 0 and unity. For a purely resistor load, the voltage and current are in phase, so that theta v minus theta I is equal to 0, power factor is equal to 1. This implies that the apparent power is equal to the average power. It's very important. In that case, all the apparent power is consumed in the actual power. So that is why I have told you that this power factor tells you how much apparent power is used as a real power. So for a purely reactive load, you can see theta v minus theta is equal to plus minus 90, power factor is 0. So in this case, average power is 0. So in these two extreme cases, power factor is said to be leading or lagging. In case of this, when theta v minus theta I is equal to plus 90 degrees, power factor is said to be lagging because current lags to voltage by 90 degrees, not voltage. We're always talking about current with respect to voltage. That is what is meant by the lagging or leading. And leading when current leads the voltage by 90 degrees, that means when theta v minus theta is equal to minus 90 degree, that means voltage is lagging to current by 90 degree, or current is leading to voltage by 90 degree. In that case, it is leading. So it is written over again. Leading power factor means the current leads the voltage, which implies a capacitive load. Lagging power factor means current lags voltage, implying an inductive load. Let us try to do one numerical. It will be quite evident from here. Series connected load draws the current of this when a voltage is applied across this. It's a series connected load. Find the apparent power, the power factor of the load. Determine the element values that are connected in series. So let us say S is equal to Vrms into Rm. What is the Vrms? That is 120 by root 2. Irms is 4 by root 2. That is multiplication of these two, we get S. Or we can say 1 by 2 into Vm into Im. That is equal to 1 by 2 into 120 into 4. That is 240 Va, not watts. The power factor is cos of theta V minus theta I. Theta V is what? Minus 20 degrees. This is 10. That is minus 30 degrees. So it comes out to be 0.866 leading. Why is this leading? Because this current leads to this voltage by 30 degrees. You can see over here, because this current has a plus 10 and voltage is a minus 20. The power factor leading because current leads the voltage. The power factor may be obtained from the load impedance as well. So load impedance is Z is equal to V by I. That is equal to 120 angle of minus 20 into 4 angle of 10. That is equal to 30 at an angle of minus 30. So this is also the power factor angle. That is minus 30. Cos of minus 30 is again equal to 0.866 leading. You can see from here, since this is minus, and we know that the minus reactance is of capacitance. So in that case, we have a capacitance whose reactance is 15 ohm. So the load impedance can be modeled as 25.9 as a resistor, since we know that real part will also always be a resistance, and reactive part can be modeled as reactance, as capacitance or inductance, depending upon the magnitude of this value, or we can say sign of this. Since this is minus, so Xc is equal to minus 15 minus 1 by omega c. So C will be equal to 1 divided by omega 15 into omega, where omega is equal to 100 pi. You can see 100 into pi is omega. So it comes out to be 212.2 microfarad. This is the value of C. So this was regarding this. So please try to do this numerical at your home. Obtain the power factor and the apparent power of the load whose Z is given when the applied voltage is this. So you need to find out the power factor, calculate I is equal to V by Z, and then from calculating I, you can find out the value of this apparent power and power factor. Now, if we have a circuit like this, in this case, we are given a voltage 3 at an 30 angle of 0. We need to find out the power factor and average power delivered to the source. This is very important. Please try to be very attentive over here. What we do, we'll first try to find out the current flowing through that is supplied by this source. In that case, we'll first find the total impedance seen by this source. It will be equal to this impedance plus the parallel combination of these two impedance, and we know that a parallel combination of these two impedance will be equal to Z1 Z2 divided by Z1 plus Z2. So total impedance will be equal to 6 plus the parallel combination of these two, 4, that is this, and minus G2. It will be equal to minus G2 into 4 divided by 4 minus G2. It comes out to be 6.8 minus J1.6. That means the total impedance seen by this source is That means this is the resistive part and this is the reactive part. And from this you can see this is the capacitive in nature. This circuit is a capacitive in nature. That means whatever be the current, you will see that current will be leading and power factor will also be leading. So this is the power factor angle. So the power factor will be equal to cos of minus 13.24. It is equal to 0.9374 leading. Since the impedance is capacitive, the RMS value of the current will be V by Z, 30 angle of 0 divided by 7 at an angle of minus 13 point this 4.286, 13.24. You can see this current leads this to this voltage by this angle. That means in that case also this is a leading circuit. So the average power supplied by the source will be Vrms Irms into power factor. Vrms is 30. It is given in the RMS values. Irms is this, because since this is RMS value, I will be also in the RMS value. It comes out to be 4.286, and power factor is this much, that is 0.9374, 0.973. It comes out to be 125 watts. This P can also be calculated I square into R, where I is the current supplied by the source, R is the resistance seen by the source. Resistance seen by the source is not only this, it is actually this resistance, because it's a combination of these two. So that will be equal to I square R. I is this, R is this. It comes again equal to be to the 125 watt, and it has to be like this. Now coming to the one more thing, that is the complex power. Actually, we come across with the instantaneous power, then average power, then apparent power. Now the complex power. Why do we get the complex power? Because it actually contains all the information, whether it's apparent power, whether it's real power, whether it's power factor, or whether it is reactive power. It has actually 4 parameters inside it. Considerable effort has been expended over the years to express the power relation as simple as possible. Power engineers have coined the term complex power, which they use to find the total effect of the parallel loads. Complex power is important in the power system analysis because it contains all the information pertaining to the power absorbed by a given load. That I have told you. Let us say we have a simple load whose voltage V is given as Vm angle of theta V and I is given as Im angle of theta I. So the complex power S that is absorbed by the load is the actually product of the voltage and the complex conjugate of the current. That I have told you earlier, that this is very important, and I will tell you in the coming slides why is it very important. So in the previous, I will go back to that slide and I will make you recall that. That's over here. I don't have to I didn't tell you that what is this 1 by 2 V into I. Just put this value and told you that the real power, the real part of this will be the average power that we are interested with. Now you can see that this 1 by 2 V into I is actually nothing but a complex power. Okay, so complex power is defined like this. Assuming that a passive sign convention, as we have to assume like this. So we're consuming this V into I, so S is equal to Vrms into Irms conjugate. So why are Vrms is equal to V by root 2, Irms is equal to Im by I by root 2, that is Irms angle of theta I. So S is equal to Vrms Irms angle of theta V minus theta I, when I have written them in terms of polar form, not in terms of phasors. So combining them or changing them to the rectangular form, it is equal to Vm Vrms Irms cos of theta V minus theta I plus J Vrms Irms sin of theta V minus theta I. So this is the same equation which we have already obtained. You can see that this part, it is the real part. Real part, it's actually nothing but the real power. And one more thing, that its magnitude, you will see that it is nothing but the apparent power. Its magnitude will be the apparent power. So hence the complex power is measured in volt ampere, because of this is also in the apparent power, is also in the volt amperes. One more thing, that angle of the complex power is nothing but the angle power factor angle. So it is the power factor angle. So you have two information which we have got, that is the complex power magnitude is nothing but the apparent power. The angle of the complex power is the power factor angle, and the complex power may be expressed in terms of the load impedance Z. So that is equal to V by I, that is Vrms by Irms, because we can divide root 2 to the numerator as well as denominator, you will get again the Vrms by Irms, that is Vrms divided by Irms angle of theta v minus theta I. So, but Vrms is equal to Z into Irms, so substituting this in this, so S is equal to Irms square into Z, or Vrms square divided by Z conjugate, so this is important, or Vrms into Irms. So in terms of impedance, so S can be equal to Vrms into Irms star, or Irms square into Z, or Vrms square divided by Z conjugate. One more thing, since Z is equal to R plus Jx, which we have already discussed, it is have a real part as well as a reactive part, or this imaginary part. So putting the value of Z over here, this S is equal to Irms square R plus Irms square into G into X. So let us call this as P. This is Irms into R, which we already discussed, that the real power is also equal to Irms square into R, and let's call this as G into Q. So it means that this Irms into X will be equal to Q. That means P is equal to real power of S, that is equal to Irms into R, and Q is equal to imaginary part of the S, that is Irms into X. So this Q is actually known as the reactive power. So P is the average or the real power, and it depends on the load resistance. Q depends on the load reactance X, and it is known as the reactive power or quadrature power. So reactive power or quadrature, reactive power means it's actually the power that is stored in the reactive elements. Quadrature power means it is in quadrature with the real power. So comparing equation this, you can see P is equal to Vrms Irms cos of theta v minus theta, which we have already calculated. So this P, which is equal to this I square R, Irms square into R. So you can see that this is equal to this. Similarly, this Q is equal to Vrms Irms sine of theta v minus theta I. The real power is the average power in watts delivered to the load. It is the only useful power. So I have told you earlier that this cos theta will determine the amount of the useful power that is actually consumed by the load. It is the actual power dissipated by the load. This is the actual power which is actually dissipated or consumed by the load. The reactive power is a measure of energy exchange between the source and the reactive part of the load. So what is actually happened? There is energy exchange. In the first half, the energy is stored in the reactive element, and next part the energy is supplied back to the source. So we can say power is a positive in the first half and power will be negative in the second half, and the net power will be equal to 0. The unit of Q is the volt ampere reactive, that is VAR. It is not watts, it is not VA, volt ampere, it is VAR, that is volt ampere reactive. To distinguish it from the real power and the apparent power, whose unit is watt and VA respectively. So what these elements, they actually does not consume the real power, they exchange the power back and forth with the rest of the network. In the same way, the reactive power is being transferred back and forth between the load and the source. Here what happens between this reactive power is actually exchange between the reactive elements and the source. So finally it represents the lossless interchange between the load and the source. So if Q is equal to 0, that means it is a resistive load, power factor will be unity. If Q is less than 0, that means it is a capacitive load, so power factor will be leading. If Q is greater than 0, that means it's an inductive load, power factor will be lagging. When Q is less than this means theta V will be less than theta I, that means current is leading, this will be negative term. So in that case it will be leading current, capacitive load, and if QV is positive, that means theta V is greater than theta I, this will be a positive term, that means current is lagging to the voltage, that means it's an inductor circuit. The complex power, which is measured in VA, is the product of the RMS voltage phasor and the complex conjugate of the RMS current phasor. As the complex quantity is real part of the power, and the imaginary part is the reactive power, Q. This shows how complex power contains all the relevant power information. So it is the standard practice to represent S, P and Q in the form of a triangle known as a power triangle. You can see it from here. This is S, this is P, and this is Q. This will be P cos of theta. Sorry, this P will be S cos of theta and Q will be S sine of theta. That is actually we are getting from this. This will be SP will be S cos of theta. Theta is the actually angle between the voltage and current, and Q will be S sine of theta, where S is the hypotenuse of the triangle. This is similar to the impedance triangle, the relationship of Z, R, and X. We have already done the impedance triangle. Similar to the angle will be the same. Here hypotenuse will be Z, this perpendicular will be X, and base will be R. Here perpendicular will be Q, hypotenuse will be S, base will be P. But this angle will be same in both the cases, because we know that power factor angle, impedance angle, and this complex power angle will be same. The power triangle has 4 items: apparent power, complex power, real power, and apparent or complex power, real power, reactive power, and power factor. As I told in the beginning, that it has 4 information hidden inside it. Given 2 items, other 2 can be obtained from the triangle. When S lies in the first quadrant, we have the inductive load and lagging power factor. This was also very important. This is the first quadrant. When S lies in this quadrant, so we have inductive load, Q is positive, and this S will have this theta V and theta Y voltage will be leading to this theta I, and current will be lagging to this voltage by some angle. In that case, it is really this inductive load when S is lies in the first quadrant. So when S lies in the fourth quadrant, the load is capacitive and the power factor is leading. So that means when this is in the fourth quadrant, Q is negative, power factor will be leading, and load will be capacitive. One more thing that is very important, that it is also possible for a complex power to lie in the second quadrant and the third quadrant. That means if this complex power lies in this quadrant, that means power is actually, this real power is actually negative. That means in that case, this real power has to be supplied back to the source, or we have a negative resistance, which is only possible in case of active circuits. You don't have to go there. For the time you just assume that we have only this complex power lying in 2 quadrants, first and fourth quadrant. First quadrant power factor will be lagging, inductive loads. Fourth quadrant power factor will be leading, capacitive load. Now let us try to do one numerical, and it will be quite easy to you to understand. The voltage across the load is given by this, and the current through the element, same element, is given by this value. And the complex power, apparent power, real power, reactive power, power factor of the load, and the load impedance. It's very simple. This voltage is given, so the RMS value will be equal to 60 by root 2 at an angle of RMS and phasor. IRMS and phasor will be given by this. The complex power will be equal to VRMS, IRMS conjugate. VRMS is this, IRMS is conjugate, taken as negative angle. So it comes out to be, when you multiply these two, it will be 90 divided by 245. This will be 60 degrees. It is the complex power. Now the apparent power simply will be the magnitude of this. The real power will be the real part of this. Real part will be 45 cos of 60 degrees. That is 45 cos 60 is 0.5. I think 22.5. Similarly, this reactive power will be 45 sine of 60 degree, and it will be minus. Minus means it will be negative. It is capacitive, and power factor will be leading. So we can express in the rectangular form to 45 cos of 22.5 and 38.97. So P is 22.5 and Q is minus 38.7. The power factor angle is this, that is cos of minus 60.5, but leading because this comes out to be negative. So it is leading because reactive power is negative. The load impedance is V by I. That is equal to V by I, 60 at an angle of 10, 5, 40 angle of 60. When this is negative, it means again it is capacitive in nature. One more thing, one important, the values may be given in different form. In this case, you can see that a load impedance that draws a 12 kV at a power factor of 0.856, lagging from a 120 volt RMS sinusoidal source. Calculate the average and the reactive power delivered to this load. Sometimes this average is known as real power or useful power or simply power. We need to find a peak current and load impedance. So given that power factor is equal to 0.856, we have in the power factor angle is the cos inverse of this. It comes out with 31.13 degrees. So This is kVA, that means this must be the apparent power, because kVA means kilovolt ampere. So apparent power is usually given in volt ampere. Since it is kVA, it means it is 12,000 VA. So that's why S is equal to 12,000 VA. So P is equal to S cos of theta. S is given as 12,000, cos of theta is given to be power factor 0.556. It comes out to be 10.272 kilowatt. While the reactive power is S sin theta, that means 12,000 into sine of theta. Theta is this. When we get the sine of theta, it comes out 0.517. It is this value. Since the power factor is lagging, the complex power will be given as S is equal to P plus GQ, that is this. This plus G times this. So this can also be obtained from here. S is equal to V into IRMS square. Okay, here we need to find out the I star, that is conjugate of I, will be equal to S divided by VRMS. S is given this divided by VRMS. It comes out to be this. This is I star. I will be equal to 100 at an angle of minus 31.13. That is over here. This is IRMS value. Peak value of the current will be equal to root 2 times this value, that is equal to 141.4 amperes. Load impedance will be simple. That is VRMS divided by IRMS. VRMS is 120 at an angle of this 0. This is IRMS. It comes out to be this, which is an inductive nature because this comes out positive. Please try this numerical at your home. This is similar. The only thing is that from kV it changes to the load changes to kVAR, and here instead of voltage, current is given. Sorry, impedance is given. So please try to find out power factor, apparent power delivered to the load, RMS, whatever you try to find out. Try to find out all the four quantities. Okay, I will stop here. Thank you.